13 billion light-years from where you're sitting right now, something is staring back at us, and it has no right to exist. The James Webb Space Telescope has reached deeper into the abyss of creation than any machine built by human hands. What it found broke every model, shattered every assumption, and left the scientific community scrambling for answers that haven't arrived yet. We're talking about galaxies that formed before they were supposed to, black holes that predate the stars themselves, worlds drifting alone through the interstellar dark, screaming in radio frequencies that no current theory can explain, signals from objects so ancient and strange that they appear to violate the most fundamental laws governing how matter, energy, and time are supposed to behave. If you've ever wanted to understand what's actually out there, what the universe looks like when you strip away, comfortable textbook version, stay right here, because by the end of this, you will never look at the night sky the same way again. We're going to go through every major discovery Webb has made that broke physics, one by one, in full detail. Some of what's coming is genuinely unsettling. Let's get into it. Something is deeply wrong with the speed of the universe. For decades, cosmologists believed they had the expansion of space figured out. Two independent measurement methods, two separate sets of calculations, and both were supposed to land on the same number. The Hubble Space Telescope provided one figure. Theoretical models built on the oldest light in the observable universe, the cosmic microwave background radiation, predicted another. The expectation was straightforward: independent methods, same answer. Instead, the two numbers flatly refused to agree with each other, and James Webb made it undeniably, irreversibly clear that this disagreement is not a calibration error. It is not a measurement artifact. It is a feature of the universe itself. Think about what it means for a balloon to inflate unevenly, the top stretching twice as fast as the bottom, despite being made of the same material, filled by the same pressure. The laws governing space-time demand that cosmic expansion happens uniformly across all of space. That's not a preference or a guideline. It's a foundational axiom baked into every model of cosmological evolution we've constructed. Webb conducted the most precise measurements of Cepheid variable stars ever achieved, pulsating stellar giants that astronomers use as standard distance markers, examining over 1,000 of them scattered across 5 separate galaxies, stretching 130 million light-years into space. The result was the same number that prior telescopes had been producing, and that number refuses to match what the cosmic microwave background independently calculates. The gap between these two figures is what cosmologists call the Hubble tension, but that name makes it sound like a minor technical disagreement between research groups. It isn't. It's a fracture line running through the foundational mathematics of modern cosmology. Either both measurement approaches are systematically wrong in the same direction, which Webb's precision has essentially ruled out, or the universe is expanding at different rates in different regions of space, in ways that the standard cosmological model cannot accommodate. Adam Riess, the Nobel laureate who has spent years tracking this crisis, stated it plainly: with measurement uncertainties eliminated, what remains is the real and deeply significant possibility that we have fundamentally misunderstood how the universe operates. Every calculated figure we rely on for the universe's age, its total size, and its ultimate fate now carries an asterisk. Webb didn't create this problem. It proved the problem is real and that it isn't going away, and that was only the first thing it found. Before we go further, if this is the kind of content you're into, make sure you're subscribed. We cover the cutting edge of astrophysics and cosmology on this channel regularly, and some of what's coming in future videos makes what we've already covered tonight look like settled science. Hit subscribe, keep it running in the background, and let's keep going. 6 objects in the ancient universe have been sitting there for 13 billion years, waiting to overturn everything we thought we knew about how galaxies form. When the Webb telescope pointed its infrared instruments at a quiet patch of sky near the constellation Ursa Major, astronomers were expecting results consistent with a universe that was barely 3% of its current age: small, clumpy, early-stage proto-galactic structures in the process of gradually assembling. Instead, they photographed 6 fully formed, enormous star systems with stellar populations rivaling our own Milky Way. 6 galaxies that had no business being that massive, that organized, and that complete at that stage of cosmic history. Astrophysicist Erica Nelson was the one who first spotted them, tiny, reddened points of light in Webb's deep field captures that turned out to be some of the most consequential objects ever photographed by any telescope. Red light in astronomy almost always means one of two things. The source is cool, or the light has been stretched and shifted toward longer wavelengths during its vast journey across an expanding universe. These objects were both ancient and impossibly luminous, a combination of properties that simply doesn't fit any existing model of early cosmic structure. Each of these 6 galaxies contained somewhere between 10 billion and 100 billion stars. To build that kind of stellar population in the time available, they would have needed to be producing new stars at rates of hundreds per year for hundreds of millions of consecutive years. Our entire Milky Way, one of the larger galaxies in our local neighborhood, produces roughly 2 new stars annually. The comparison isn't even in the same order of magnitude. The research team informally nicknamed them the Universe Breakers, and the name is apt. Every simulation ever run of early cosmic structure formation is built on the same foundational assumption, that large-scale structure assembles slowly. Dark matter halos collapse first, pulling in regular matter. Gas clouds contract under gravity and ignite the first stars. Those stars group into protogalaxies. Protogalaxies merge into intermediate structures. Those structures gradually grow into mature galaxies over billions of years through hierarchical assembly. These 6 objects compress that entire timeline into a fraction of the expected duration. The unavoidable implication is either that dark matter behaved far more aggressively in the early universe than any simulation has ever captured, or that some mechanism for rapid stellar assembly exists that cosmology has never identified or theorized. Joel Leger, one of the scientists who analyzed these objects, stated the problem directly. We looked back to the very beginning of cosmic time and found something so unexpected that it creates genuine problems for the field. Follow-up spectroscopic observations, designed to confirm whether these were truly massive early galaxies or some foreground confusion, only deepened the problem. While astronomers were still processing what those 6 galaxies meant, Webb found something even harder to explain: a supermassive black hole with almost no galaxy around it, wandering through the early universe essentially alone. The object contains the equivalent mass of 50 million suns, compressed into a region smaller than our solar system. It exists just 600 million years after the Big Bang, and it is surrounded by almost no stellar population. A naked gravitational monster drifting through the primordial cosmos with no host, no company, and no obvious explanation for how it got there. Standard black hole formation theory requires a sequence of events that takes time. First, you need the initial generation of massive stars to coalesce from the primordial hydrogen and helium gas. That alone takes hundreds of millions of years. Then those stars need to live out their brief, violent lives, die in supernova explosions, leaving behind compact stellar remnants. Those remnants must then grow through accretion and merger events over additional hundreds of millions of years before approaching the supermassive category. The full sequence, under standard assumptions, takes longer than the universe had been alive at the epoch where Webb found this object. Roberto Maiolino, the Cambridge astrophysicist who helped characterize the discovery, described it as completely off the scale, an object that sits outside every theoretical framework his team had developed for early black hole formation and evolution. 3 competing explanations have been put forward, and each one is stranger than the last. The first suggests that under precisely the right conditions, enormous clouds of primordial gas can bypass the stellar formation phase entirely and collapse directly into a black hole, skipping millions of years of stellar evolution in a single gravitational event. The second proposes that some early black holes found mechanisms to consume surrounding matter at rates far exceeding what current physics permits, growing to supermassive scale in a fraction of the time standard accretion models require. The third explanation is the most disturbing. This object may be a primordial black hole, not the product of stellar collapse at all, but something that formed from violent density fluctuations in the primordial plasma that filled the universe within its first 5 seconds of existence, before any stars had ever ignited. If that's true, this black hole has been drifting silently through the cosmos for over 13 billion years, lurking in the dark long before the first photon of starlight ever reached it. Webb has found hundreds of similar compact, reddened objects scattered through the early universe. Each one represents the same problem. Each one demands the same answer that we don't yet have. The concept of primordial black holes opens a door that cosmology has historically been reluctant to walk through. A team led by Andrea Ferrara at the Scuola Normale Superiore in Pisa proposed that black holes, not stars, may have been the first significant sources of luminosity in the universe. If regions of the primordial plasma reached sufficient density fluctuations and collapsed directly into black holes within the first moments after the Big Bang, those objects would have been sitting in the dark, growing silently, for hundreds of millions of years before the first stellar populations ever switched on. When gas eventually began falling into these ancient monsters, the superheated accretion material would have glowed, potentially producing signatures that Webb, looking back at the early universe, might be misinterpreting as signs of stellar populations. Some of the point-like luminous objects Webb sees in the deep early cosmos may not be galaxies of stars at all. They may be the feeding frenzies of black holes that have existed since the first instance of creation itself. The implications of this stretch in multiple directions. If primordial black holes were common in the early universe, statistical models suggest that some fraction of them would have remained relatively small enough to still be out there today, invisible, scattered through the Milky Way and detectable only through their gravitational influence on surrounding matter. These wouldn't be rare theoretical curiosities, they'd be a component of our local galactic environment. The detection of even one confirmed primordial black hole would provide a direct observational window into conditions during the universe's first seconds, timescales and energy densities so extreme that no particle accelerator or laboratory experiment can approximate them. That single confirmed detection would be, arguably, the most significant physics discovery in human history. Webb also captured an event that cosmologists had theorized for years but never directly observed: the real-time formation of a supermassive black hole through direct gravitational collapse. The system involved a striking pair of colliding galaxies that researchers have nicknamed the Infinity Galaxy for the figure 8 pattern created by their dual cores and surrounding gas rings, hosted a black hole discovered suspended in gravitational no man's land between the two galactic nuclei. In a normal galaxy merger, the supermassive black holes from each galaxy spiral toward each other over millions of years and either merge into a single, more massive object, or in some cases, one gets gravitationally ejected from the system entirely. The Infinity Galaxy breaks this pattern completely. Its black hole sits precisely between the two cores, in a position that standard gravitational dynamics says should be unstable. Peter van Dokkum and Gabriel Brammer identified the system through Webb's deep field imaging and confirmed the black hole's presence and location through radio emission signatures. The formation mechanism the data points to is called direct collapse. When the two galaxies collided, the enormous streams of gas flowing between their nuclei reached densities sufficient for direct gravitational implosion into a black hole. No stellar phase, no stellar remnants, no millions of years of intermediate evolution required. The collapse happened directly from gas to supermassive object. The black hole is now actively feeding on the material, bridging the two galactic cores, growing larger in real time as astronomers watch. What makes this discovery significant beyond its visual drama is what it implies about the early universe. Galaxy mergers were far more frequent in the cosmos's youth, when galaxies were more numerous and more densely distributed. If direct collapse black hole formation occurs during mergers, then the early universe was an environment constantly manufacturing supermassive black holes through rapid, violent events, which would explain why Webb keeps finding them already enormous at epochs when they shouldn't have had time to grow through conventional pathways. Out in the Orion Nebula, one of the closest stellar nurseries to Earth, Webb documented the existence of over 50 free-floating planets, worlds with no host star, no fixed orbit around anything, drifting through the nebula in the gravitational framework of the nursery itself, rather than any individual stellar system. These aren't small rocky objects. Most of them are roughly Jupiter mass, gas giants that appear to have been ejected from young planetary systems during the dynamically chaotic early phases of stellar formation, when gravitational interactions between newly formed worlds frequently result in one or more being hurled out of the system entirely. What nobody expected to find was that dozens of these ejected worlds travel in pairs, two planets bound to each other gravitationally, orbiting their shared center of mass through the interstellar medium with no star anywhere in the picture. Scientists have named them Jupiter mass binary objects, JOES, and they represent a category of astronomical object that had not previously been confirmed to exist. The formation of binary rogue planets is, theoretically, extraordinarily difficult to achieve. For two ejected planets to end up in mutual orbit, they need to be expelled from their original system at nearly identical velocities and angles, and then somehow enter a gravitational capture arrangement rather than simply flying apart into separate trajectories through space. The probability of this happening even once should be vanishingly small, yet Webb found dozens of them in a single stellar nursery, which means the mechanism responsible isn't a freak coincidence, but something more systematic, something that current planet formation models failed to predict. The mystery deepened further when radio observations of these wandering pairs revealed gigahertz-range radio emissions coming from several JMBOs, signals at frequencies thousands of times higher in pitch than FM radio broadcasts produced by worlds with no star, no ionosphere, and no obvious, conventional explanation for electromagnetic output at that intensity. The working model involves complex magnetic field interactions generated by the tide forces the two worlds exert on each other, two massive gas giants in perpetual gravitational conversation, functioning as enormous electromagnetic generators through their orbital dynamics. Different pairs produce different radio signatures, each binary system appearing to have a unique electromagnetic fingerprint. The existence of hundreds of these objects in one nebula implies billions more throughout the galaxy, permanent cosmic orphans, broadcasting into the dark on their own terms. In the star-forming region NGC 6357, Webb's near-infrared spectrograph analyzed the protoplanetary disk surrounding the young star XUE-1 and found something that planetary science had no framework to account for. In the inner disk, the zone where rocky, potentially habitable planets form, the telescope detected carbon dioxide as the dominant compound with water vapor barely detectable at all. Every model of terrestrial planet formation is built on the assumption that water is one of the most abundant molecular ingredients in this critical zone. The XUE-1 system doesn't have it. The planets assembling there are being built from fundamentally different raw materials than any world in our solar system. Two explanations exist, and both have significant implications. One holds that intense ultraviolet radiation from XUE-1 itself or from the cluster of massive stars nearby in NGC 6357 has photodissociated the water molecules in the disk, breaking the bonds between hydrogen and oxygen atoms and driving the hydrogen away while the oxygen recombines with carbon into CO2. The other proposes that the specific thermal and chemical history of this disk produced dust, grains coated in carbon dioxide ice rather than water ice, creating a chemical environment unlike what planet formation models have been built to handle. Either way, the worlds forming in the XUE-1 system will be chemically alien, with atmospheric and geological processes that have no analogue anywhere in our local stellar neighborhood, built from ingredients and in conditions that planetary science has never modeled. And if UV environments can strip water from disk regions around young stars, the galactic implications are substantial. Rocky planets lacking the chemical building blocks that terrestrial habitability depends on may be far, far more common throughout the galaxy than anyone had assumed. 55 Cancri E is a world that defies every expectation about what a planet can be and still sustain an atmosphere. It orbits its host star in just 18 Earth hours, close enough that the same hemisphere faces the star permanently, creating a day's side with surface temperatures exceeding 4,000 degrees Fahrenheit, hot enough to vaporize silicate rock, hot enough to liquefy copper, hot enough to flash most known solids into plasma. By every standard model of atmospheric physics, this planet should be as bare as Mercury. Any original atmosphere would have been stripped to nothing within millions of years by the constant particle bombardment and radiation flux from a star that close. The models are unanimous on this point, or they were. Webb's mid-infrared instrument found something different. Temperature readings from the day side came in substantially cooler than the models predicted, and the only mechanism capable of producing that discrepancy is an atmosphere thick enough to redistribute heat from the star-facing hemisphere to the permanently dark night side through large-scale atmospheric circulation. Something is blanketing this world and moving energy around it. Spectroscopic analysis pointed to carbon monoxide and carbon dioxide as the dominant atmospheric components, heavy, stable molecules that can survive extreme radiation environments far more effectively than lighter gases. The current leading model is that 55 Cancri's atmosphere isn't a primordial remnant at all. It's being continuously manufactured by the planet's own interior, which is being cooked by the tidal forces of its extremely close-in orbit, driving volcanic outgassing on a scale that continuously replenishes whatever the star destroys. Picture a world where the crust itself is perpetually boiling, vaporized rock rising from the surface, swept across the planet by supersonic winds, condensing as liquid mineral rain on the night side, then re-evaporating and cycling back. A world that has become a planetary-scale distillation apparatus, sustaining an impossible atmosphere through an equilibrium between destruction and geological production. Its existence forces a complete reconsideration of what atmospheric chemistry can survive and under what conditions. 3I Atlas is the third confirmed interstellar object ever detected passing through our solar system, and it is by a substantial margin the most ancient. Roughly 7 miles across, composed of ice and rock, it entered the solar system on a trajectory originating from the direction of the Milky Way's thick disk, a region populated predominantly by old stars that formed in the galaxy's youth. Webb's near-infrared spectrograph analyzed the chemical composition of the extended coma surrounding its nucleus and found carbon dioxide as the dominant volatile compound, rather than the water vapor that characterizes comets from our own system. Combined with the object's speed, over 130,000 miles per hour, and its gravitationally unconstrained trajectory, the data pointed to an origin age of approximately 7 billion years. This object is 3 billion years older than the Earth. It is older than the Sun. It formed around a star that ceased to exist billions of years before our solar system came into being, likely destroyed by the supernova that ended that star's life, an explosion that flung this fragment of a dead solar system into interstellar space on a trajectory it has been following ever since. For 7 billion years, this comet drifted through the galaxy, crossing distances that dwarf anything in human experience, carrying locked within its ice a chemical record of a stellar environment that no longer exists and that no other observable object can directly represent. The galaxy it traveled through during those 7 billion years was different at each stage of the journey, more crowded early on, more quiescent later, steadily enriching itself with heavy elements from successive generations of dying stars. 3I Atlas passed through all of it. Statistical models suggest that dozens or hundreds of similar ancient interstellar travelers cross through the inner solar system at any given time, undetected because current survey programs are not optimized to catch them. Each one is a messenger from a civilization of worlds that no longer exist. Webb's deep field surveys have revealed approximately 300 objects that astronomers cannot classify using any existing framework. They appear as tiny, reddened point sources scattered through images of the early universe, compact, enigmatic, and far more luminous than anything current theory predicts for the first billion years of cosmic history. Researchers call them little red dots, and they have become one of the most actively debated mysteries in contemporary observational astronomy. A research team at the University of Missouri catalogued over 300 of them from Webb data, each displaying a combination of extreme distance, compact morphology, and extraordinary energy output that matches no known category of astronomical object. Some appear point-like under careful analysis, suggesting they may be powered by supermassive black holes in states of extreme accretion rather than distributed populations of newly formed stars. Others show faint evidence of extended structure consistent with genuine galaxy morphologies. But galaxies undergoing star formation at rates so far beyond current predictions that the models themselves become untenable. The most disquieting possibility is that these objects represent a phase of cosmic evolution that simply has no modern equivalent, that the physical conditions of the universe's first billion years, denser and hotter and chemically simpler than today's cosmos, permitted the formation of entire classes of luminous objects that cannot exist in the universe as it currently stands. Bang Jangson, the graduate student leading the Missouri team's analysis, made the stakes explicit. Even a small number of confirmed little red dots in the early universe will force revisions to existing theories of how galaxies form and evolve. There are 300 of them in the data. The revisions required may be substantial. Among the most philosophically disorienting findings in Webb's entire portfolio is the discovery that galaxies separated by distances so vast that no causal signal could ever have passed between them are rotating in statistically correlated directions. In the Advanced Deep Extragalactic Survey, researchers analyzed 263 galaxies and found alignment patterns in their rotational orientations that exceed what random chance could account for. These galaxies are too far apart to have influenced each other gravitationally. Light from one would take millions of years to reach another. There is no mechanism in standard cosmology through which their spins could have been coordinated. And yet the coordination is there in the data. Computer scientist Leo Shamir, who led the analysis, identified two frameworks that could account for the observation, and both are genuinely disturbing for the current cosmological picture. The first, the universe was born with angular momentum. If the Big Bang itself emerged with a preferred rotational direction, that bias would have been imprinted on the geometry of space-time from the very beginning and subsequently inherited by the galaxies that formed within it over billions of years. This explanation fits naturally within black hole cosmology. The hypothesis that the observable universe is the interior of an enormous black hole, existing within a larger parent cosmos, inheriting the rotational characteristics of the parent object at the moment of formation. The second possibility is worse for conventional physics. If the universe didn't begin rotating, then some unknown field or force is coordinating galactic motion across scales larger than anything current cosmological models have a mechanism to address. The coordinated spins also carry implications for dark energy. If space itself has a preferred rotational axis, the mysterious force driving cosmic expansion may not be uniform in all directions, which would naturally produce the kinds of expansion rate discrepancies that Webb has been cataloguing throughout its survey operations. Deep in Webb and Chandra X-ray Observatory data, researchers found a supermassive black hole that is actively feeding at 40 times the rate that physics says is possible. The object is designated LID 5568, and it was buried among thousands of X-ray sources in the deep field observations. Invisible to optical instruments but blazing in high-energy radiation, detectable only through Webb's infrared sensitivity combined with Chandra's X-ray data. Its accretion rate continuously violates the Eddington limit by a factor of 40. The Eddington limit is not a soft guideline or a rule of thumb. It is the theoretical maximum rate at which any black hole can consume surrounding matter, derived from the point at which radiation pressure from superheated infalling gas becomes sufficient to blow away the food supply and arrest further accretion. LID 568 exceeds it by a factor of 40 continuously. Think of it this way: every black hole has a maximum drinking rate. Beyond that rate, the pressure from the heat it generates while drinking blows away the cup. LIDE 568 is drinking from 40 cups simultaneously. The black hole exists just 1.5 billion years after the Big Bang, at an epoch when objects grown through standard stellar death pathways shouldn't have had time to accumulate anywhere near its mass. Its extreme feeding rate provides the only plausible explanation. Brief but catastrophically intense growth episodes that added enormous mass in cosmically short timeframes, bypassing the slow accumulation model entirely. How the black hole stabilizes its accretion disk against the radiation pressure that should theoretically be destroying it remains unresolved. Either the geometry of the surrounding material provides some shielding effect that current models don't capture, or matter under those conditions possesses properties we haven't identified. LIDE 568 is, in the most literal sense, available in physics, doing something that the laws governing its behavior say it cannot do. Webb has also catalogued what researchers are calling sleeping beauty galaxies, massive, well-developed star systems distributed through the early universe that have inexplicably ceased forming stars. These objects appear during what should have been the most energetically active periods of their development, epochs when the universe was dense, with raw gas and the dark matter concentrations needed to fuel vigorous stellar nurseries were readily available, and yet these galaxies sit dormant. Their existing stellar populations age. No new stars are being born. Whatever construction process built them stopped, and stopped early. The leading candidate explanation involves AGN feedback, the possibility that the supermassive black holes at the centers of these galaxies became so energetically active that the radiation and particle jets they produced heated the surrounding gas to temperatures above the threshold at which it can collapse and form new stars. But the timeline creates problems. Some of the dormant galaxies appear to have gone quiet before their central black holes reached the activity levels required to cause that kind of galaxy-wide suppression. A second theory proposes that an initial burst of star formation so intense it defies current efficiency models simply consumed all available gas before the galaxy had time to develop the regulatory mechanisms that sustain long-term star formation in most systems. A third possibility, and the one that current data cannot rule out, is that some quenching mechanism operated in the early universe under conditions that no longer exist anywhere in the modern cosmos. A process that we have never observed because the universe has moved past the conditions that made it possible and may never permit it again. The free-floating world designated SIMP 0136 plus 0933 gave Webb one of its most detailed atmospheric portraits ever obtained of any planet. This object drifts through space without a host star, sustained only by its own residual heat from formation and the tidal energy generated by its rapid rotation. Webb's infrared instruments resolved a layered atmospheric structure unlike anything previously documented in planetary science. Iron clouds occupy the lower atmospheric layers, not water vapor, not ammonia, not methane, but iron, with a second cloud layer composed of forsterite, a magnesium silicate mineral typically found in meteorite samples, sitting at higher altitudes. The two cloud systems operate according to different circulation dynamics, creating a three-dimensional atmospheric structure that shifts and evolves as the planet rotates. Above both cloud layers, Webb detected regions of anomalous localized heating that appear to be driven by radio aurora activity, electromagnetic phenomena powered by the planet's extraordinarily strong magnetic field interacting with charged particles drifting through the surrounding interstellar medium. These auroral systems heat portions of the upper atmosphere to temperatures that exceed those found within the metallic cloud layers below. The entire atmospheric system is dynamic, patchy, and continuously evolving, driven not by a star's energy input, but by internal heat, rotation, and magnetic field interactions with the surrounding interstellar environment. Alison McCarthy, the graduate student leading the atmospheric analysis, noted that the variability mechanisms observed had been theorized but never directly confirmed. If one rogue planet adrift in interstellar space can sustain atmospheric complexity at this level, the range of planetary environments capable of supporting active chemistry and weather systems is far broader than planetary science had been operating under. Webb has revealed the full scale of galactic violence in cluster environments through its observations of what researchers call jellyfish galaxies, systems that leave elongated tentacles of gas and stars streaming behind them as they move through the dense, superheated medium that fills the space within galaxy clusters. The cosmic owl galaxy is one of the most visually arresting examples. Its two bright nuclear regions create the impression of a pair of enormous eyes, while the surrounding strip material forms extended filaments trailing hundreds of thousands of light years in the direction opposite the galaxy's motion. These are not decorative structures, they are evidence of physical destruction in progress. Ram pressure, the cosmic headwind generated as a galaxy moves at high velocity through the hot intracluster gas, is literally tearing the galaxy apart, stripping away the outer layers of its gas reservoir and a portion of its stellar populations. Webb's infrared sensitivity revealed something unexpected within those stripped tentacles: active star formation. The same ram pressure that destroys the galaxy's outer structure is also compressing stripped gas into densities sufficient to trigger the collapse of new stellar nurseries in gravitational isolation, producing young, massive, blue stars billions of light years from any galaxy that could claim them. The cosmic owl is simultaneously being destroyed and creating new stellar generations in the debris of its own dismemberment. The frequency of jellyfish galaxy morphologies throughout Webb's cluster observations indicates that this kind of stripping-driven destruction is not an exotic edged case. Galaxies navigating through cluster environments lose mass continuously, scattering stellar populations across intergalactic space and contributing a continuous rain of orphaned matter to the voids between galactic systems. Stars throughout the cosmos are consuming each other, and Webb has captured those events in unprecedented detail. Binary star systems, pairs of stars sharing a gravitational bond, frequently end with one member feeding on the other, and Webb's infrared vision cuts through the gas and dust that previously obscured these events from direct observation. The range of outcomes is extraordinary. When a white dwarf, a dense stellar remnant roughly Earth-sized but containing the mass of a full star, accretes enough material from a companion, it triggers a thermonuclear detonation that temporarily outshines billions of ordinary stars. When a neutron star or black hole consumes a companion, the result can be a kilonova, an explosion that synthesizes heavy elements including gold, platinum and uranium in the extreme density of the merger, while simultaneously producing a gamma-ray burst detectable across billions of light years. Webb has documented the complete arc of these cannibalism events, from initial material transfer through escalating accretion to the final explosive conclusions, capturing the stages of stellar consumption that previous telescopes could only infer from indirect evidence. Perhaps the most significant implication of this documentation is what it reveals about the origin of the elements. The heavy elements that make up a substantial portion of the material world, the gold in electronics, the platinum in catalysts, the iodine in biological systems, were not produced in stellar interiors and scattered by ordinary supernovae. They were forged in the extreme violence of compact object mergers, in moments so energetic that they briefly outshine entire galaxies. Webb is watching these events happen. The universe is still making the elements that complex chemistry requires in explosions powerful enough to be seen from across the observable cosmos. The Milky Way's own central black hole, Sagittarius A, a 4 million solar mass object at the galaxy's core, was monitored continuously by Webb for a total of 48 hours across multiple observation sessions. What the telescope found contradicted the relatively placid picture that previous observations had established. Sagittarius A is not the quietly feeding, occasionally active black hole that textbook descriptions suggest. It is in a state of continuous irregular flux, with its accretion disk producing an uninterrupted sequence of brightness variations punctuated by sudden, massive flares that appear without warning and subside just as unpredictably. Farid Yousefzadeh at Northwestern University, who led the observation campaign, described the behavior as genuinely unlike anything previously observed in a supermassive black hole of comparable mass a system that generates no discernible pattern and conforms to no model his team applied to it. The short-term brightness variations likely originate in magnetic turbulence within the accretion disk. Plasma compressed and agitated by field line interactions, producing localized flashes of radiation in the superheated gas spiraling toward the event horizon. The larger, more dramatic flares suggest something more violent, discrete condensed regions of matter crossing the photon sphere, the boundary region where the curvature of space-time is so extreme that light itself begins to orbit the black hole before either escaping or crossing the event horizon permanently. The chaotic character of these flares suggests that Sagittarius A is consuming matter in irregular, unpredictable episodes rather than through the steady accretion processes that standard models describe. The brightness variations originate in a region where space-time distortion is so severe that general relativity is operating at the absolute edge of its predictive validity, a zone where quantum effects may be influencing the behavior of classical matter in ways that no existing theoretical framework can fully account for. Our own galactic center is running physics experiments that we don't yet have the mathematics to describe. Young star systems throughout the deep early universe have been found producing heavy element abundances that shouldn't be possible given their apparent age. Standard stellar chemical evolution is a generational process. First-generation stars form from hydrogen and helium, fuse heavier elements in their cores over millions of years, then die in supernova explosions that distribute those newly synthesized elements into the surrounding interstellar medium. Second-generation stars form from that enriched gas. The process repeats across many stellar generations and billions of years, gradually building up the abundance of heavy elements in the universe's chemistry. Webb found galaxies less than 1 billion years old that display metallicities, heavy element concentrations, that standard theory says require multiple rounds of stellar birth and death to accumulate. The galaxy JSGSC 1311, observed just 330 million years after the Big Bang, showed spectroscopic signature indicating it had already undergone substantial chemical enrichment at an epoch when the universe should have barely completed its first stellar generation. The two explanations being seriously considered are both cosmologically significant. One proposes that the first generation of stars were vastly more massive than anything that forms today, stellar objects potentially hundreds of times more massive than our Sun, burning so intensely through their fuel that their entire lives lasted only a few million years before exploding in hypernova events that distributed enormous quantities of heavy elements across vast volumes of space in a single catastrophic moment. Such extreme stars appear impossible in the modern universe, where the higher metallicity of molecular clouds and the physics of gas cooling prevent their formation. But the conditions of the early cosmos, hotter, simpler, chemically purer, may have permitted them, and their existence would solve several of Webb's early universe puzzles simultaneously. The second explanation is more unsettling. Some enrichment process entirely outside of stellar nucleosynthesis may have been operating in the early universe, producing heavy elements through mechanisms that current physics does not account for. If that's true, the textbook story of how the universe built its chemistry from the ground up is missing a chapter. The full weight of what Webb has discovered comes into focus when you consider all of these findings together. The anomalous expansion rates, the impossible early galaxies, the primordial black holes, the naked wandering singularities, the coordinated galactic rotations, the rogue planets broadcasting radio signals, the stars building chemistry ahead of schedule, the black holes feeding at impossible rates. No single one of these findings is a minor anomaly. Each one, standing alone, would require significant revision to at least one core assumption in our understanding of how the universe works. Taken together, they form a pattern, and that pattern points toward a cosmos that is fundamentally more complex, more dynamic, and more structurally alien than the models built across the last century of cosmological progress were designed to capture. The rotational coordination of galaxies across millions of light years and the asymmetries in cosmic expansion both point toward the same deeply uncomfortable possibility that our observable universe may not be a self-contained system, that it may exist within a larger structure, subject to physical influences from outside the boundary we can observe. The black hole cosmology hypothesis, that the Big Bang represents our universe crossing the event horizon of a supermassive object in a parent cosmos, inheriting its angular momentum, experiencing its expansion as an artifact of falling toward a singularity in higher dimensional space, fits the observational evidence with a consistency that is difficult to dismiss as coincidence. In this framework, dark energy is not a substance or a property of empty space. It is the increasing curvature of space-time around us as we fall deeper into the parent object. The Hubble tension is not a measurement error. It reflects the fact that different observational methods are inadvertently measuring different aspects of motion through curved space-time in a parent gravitational field. The coordinated galaxy spins are not mysterious. They are the inheritance of the parent black hole's angular momentum, imprinted on our universe at the moment of its formation. None of this means physics is broken. It means our current version of physics is incomplete, a high-quality approximation that works within a certain range of conditions and breaks down beyond them, as all approximations eventually do. Every anomaly Webb has produced is also a target, a specific, concrete observational fact that any successor theory must account for. The process of science doesn't retreat from this kind of evidence. It incorporates it. The shattering of a cosmological model is the beginning of a better one. What Webb is doing, observation by observation and discovery by discovery, is constructing the body of evidence that the next generation of physical theory will have to reckon with. Evidence gathered at a precision and depth that no previous instrument could achieve. The universe is stranger than we thought. It is also more specific, more detailed, and more available to direct observation than any generation of astronomers before this one ever had access to. Whatever it actually is, however it actually works, Webb is getting us closer to finding out, and the closer it gets, the more extraordinary the answers become. Whatever you believe about the night sky after tonight, one thing is certain: the comfortable, orderly, comprehensible cosmos described in textbooks no longer exists. Webb replaced it with something real, and real turns out to be far more interesting. Webb has also delivered its most disturbing documentation of dark matter's role in cosmic violence through observations of galaxy clusters in the process of colliding. These are events that release energies comparable to billions of simultaneous supernova explosions. But most of the violence is invisible. When two galaxy clusters collide, their hot gas interacts electromagnetically, slowing and heating until X-ray observatories can detect it. But the dark matter halos of both clusters, comprising the vast majority of the cluster's total mass, pass through each other almost without interaction, continuing forward as if the collision barely registered. The result is a physical separation between the visible matter and the dark matter that makes the presence and distribution of each independently measurable. Webb's imaging has revealed the full extent of disruption these events caused to individual galaxies caught in the collision zone. Galaxies located millions of light-years from the direct collision axis show evidence of gravitational disturbance consistent only with dark matter, interactions operating on scales previously not incorporated into merger models. Vast stellar streams, elongated rivers of stars stretching for millions of light-years, connect and radiate from galaxies throughout the collision region, representing the torn remnants of galactic structures that have been gravitationally shredded by dark matter tidal forces during the merger event. Webb's infrared sensitivity has revealed the full extent of these stellar streams for the first time, showing spiderweb-like networks of disrupted matter that previous telescopes were too insensitive to detect in their faint infrared glow. The scale of destruction implied suggests that dark matter doesn't merely provide passive gravitational scaffolding for cosmic structure. It participates actively in reshaping galaxies through tidal forces and gravitational interactions that can disperse stars across intergalactic space on timescales shorter than a single orbital period of the Milky Way. The most extreme example of spacetime distortion in Webb's observational catalogue involves a galaxy so massive and so dense that its gravitational field bends the fabric of space into a configuration that produces multiple distinct images of a background object lying far behind it. Webb detected at least 4 separate images of the same background galaxy, projected across the cosmic sky by the gravitational lens, each one magnified to a different degree, and, because light traveling along each bent path covers a different distance, showing the background galaxy at a different moment in its history. One image shows the galaxy as it appeared approximately 800 million years ago. Another reveals its structure more than 1 billion years in the past. The lensing galaxy has effectively created a natural time machine displaying the evolutionary history of a single star system across multiple epochs simultaneously. What makes this discovery genuinely disturbing for cosmological models is what the lensing geometry implies about the distribution of dark matter in the lens galaxy. To produce space-time curvature severe enough to generate 4 distinct images of a background source, the dark matter concentration within this galaxy must be far denser and more sharply structured than any standard dark matter halo model predicts. Webb's analysis of the lensing patterns detected substructure within the dark matter distribution, clumps and density variations on scales that current theories of dark matter particle physics say should not exist. If dark matter halos contain internal substructure at these scales, the interactions between dark matter and normal matter during galaxy formation were more complex and more violent than our models have assumed. The time delay measurements between the different lensed images also provide some of the most precise direct observational tests of general relativity's predictions for space-time curvature ever obtained, and the results push those tests into regimes where quantum gravitational effects might begin to become relevant. Running through all of Webb's discoveries is a thread that points towards something even more fundamental than any individual anomaly: the accumulating evidence that space-time itself, under sufficiently extreme conditions, becomes structurally unstable. Gravitational lensing effects around certain massive objects show small but persistent deviations from the precise predictions of general relativity. Unexplained energy signatures appear in regions near black hole event horizons where quantum mechanical effects should, according to current theory, be too weak to influence classical space-time geometry at observable scales. Webb has identified several candidate gravitational lensing patterns that cannot be explained by any known distribution of matter or energy, and that are consistent with what theoretical physicists call cosmic strings, hypothetical one-dimensional defects in space-time that could have formed during phase transitions in the early universe, permanent scars from the cosmos's violent birth that remain as structural anomalies woven into the geometry of space itself. The convergence of all these discoveries produces a picture of a universe operating far closer to the edge of physical stability than any prior generation of astronomers had reason to suspect. The early cosmos was not the gentle, orderly environment that textbook versions of the Big Bang narrative implied. A smooth, hot plasma gradually cooling and structuring itself through well-understood gravitational collapse over billions of years. It was a place of catastrophic violence where primordial black holes lurked before the first stars existed, where galaxy-scale structures assembled in timescales that current physics cannot account for, where black holes consumed matter at rates that violated the laws governing them, and where the chemistry of planetary formation diverged from the template that our own solar system was built to represent. Webb is not finding the universe we expected to find. It is finding the universe that was actually there, hidden beneath the limits of every instrument that came before it. Every discovery Webb has made adds to a growing body of evidence that the cosmos we inhabit is both more ancient in its violence and more structured in its complexity than our models anticipated. The primordial black holes that may have predated the first stars, the galaxy formation processes that compressed billions of years of assembly into hundreds of millions, the coordinated rotations of galaxies across distances no physical signal could bridge, the black holes feeding at impossible rates, the rogue worlds broadcasting electromagnetic signatures that no planetary physics had predicted, the stars at the centers of galaxies consuming their companions in explosions that forge the materials that planets and organisms are built from. The universe Webb reveals is not the universe of the textbooks. It is the universe as it actually is, violent, ancient, far stranger than our intuitions were built to handle, and far more detailed and specific than the smoothed-out models that preceded it ever captured. This is what makes the James Webb Space Telescope unlike every other scientific instrument in history. It isn't just more sensitive than its predecessors. It isn't just higher resolution or more broadly capable across multiple wavelength ranges, though it is all of those things. It is capable of testing ideas at the actual scales and epochs where those ideas make specific predictions, and it has returned repeatedly and consistently with observations that those predictions fail to anticipate. That is not a failure of the telescope. That is the telescope doing exactly what it was built to do. And every time it finds something that breaks a model, it is also providing the specific observational data that the next model will have to be built to explain. Science advances not when experiments confirm what we expect, but when they find something we didn't. By that measure, James Webb is the most productive scientific instrument ever pointed at the sky, and it has years of observation time still ahead of it. What you do with the universe Webb reveals is, in the end, a personal choice. You can find it disorienting, the stable, comprehensible cosmos replaced with something stranger and harder to hold, or you can find it exactly what it is, the most detailed and honest portrait of reality that the human species has ever produced. A universe that doesn't owe us comprehensibility. That operates according to principles we are still in the process of discovering. That contains objects and processes and histories that no civilization of human beings had ever directly observed before this decade. Every discovery Webb makes is a gift, even the disturbing ones, especially the disturbing ones, because the disturbing discoveries are the ones that are actually true. The universe James Webb has revealed is strange, violent, ancient, and vast beyond any meaningful conceptual grasp. But it is also, for the first time in human history, directly observable, and we are the generation that gets to watch it come into focus. To truly appreciate how alarming the Hubble tension is, you have to understand what cosmologists were expecting when Webb came online. The standard model of cosmology, called lambda CDM, for cold dark matter with a cosmological constant, had been refined across decades of observation into what many considered a near-complete description of how the universe evolves. It predicted the abundance of light elements produced in the first minutes after the Big Bang. It predicted the pattern of temperature fluctuations in the cosmic microwave background. It predicted the large-scale distribution of galaxies across the cosmos on every test it passed. The assumption going into Webb's measurements of Cepheid stars was that the telescope would simply confirm, with greater precision, the expansion rate that previous ground-based and Hubble Space Telescope measurements had already established. What happened instead is that Webb locked down the precision of those measurements so firmly that the error bars shrank to almost nothing, and with smaller error bars, the gap between the two independent measurements of the expansion rate didn't narrow. It became undeniable. The two values in tension are approximately 67 and 73 kilometers per second per megaparsec. Those numbers measure how fast space is expanding between any 2 points separated by a megaparsec, roughly 3.26 million light-years. The lower number comes from calculations based on the cosmic microwave background, the oldest light in the universe, imprinted on the sky when the cosmos was just 380,000 years old. The higher number comes from direct measurements of the local universe using distance markers like Cepheid variables and Type Ia supernovae. The difference between 67 and 73 might seem minor in everyday terms. In cosmological terms, it is an enormous theory-breaking discrepancy. If the universe expands at 73 but the CMB predicts 67, then either our understanding of the early universe is wrong, our understanding of the local universe is wrong, or, most disturbing, both are right and the universe genuinely expands at different rates in different contexts, which would require an entirely new physical ingredient to explain. Some of the proposed solutions are almost as unsettling as the problem itself. One class of hypothesis introduces what physicists call early dark energy, a form of energy that existed in the early universe, temporarily changed the expansion rate during a critical period before the CMB was imprinted and then faded away. If this existed, it would shift the CMB predicted value upward toward the locally measured one. But early dark energy requires the existence of a new fundamental field that nobody has detected and that has no grounding in any current particle physics theory. Another class of hypothesis proposes that dark energy, the mysterious force driving the current accelerating expansion of space, is not constant across time or space, but dynamic, changing its strength as the universe evolves. A time-varying dark energy would mean that the cosmological constant, that in lambda CDM, isn't a constant at all, and that the entire mathematical framework built around it needs rebuilding from the foundation. Webb's measurements haven't resolved which of these explanations is correct. What they have done is close off the most comfortable explanation, that it was all a measurement error. The 6 universe-breaker galaxies aren't simply an isolated puzzle. They represent the tip of a much larger problem that Webb has been accumulating evidence for since its first deep field observations. When astronomers build simulations of cosmic structure formation, running the equations of gravity, dark matter dynamics, gas cooling, star formation, and feedback processes forward from the initial conditions of the early universe, the simulations consistently produce a cosmos where the most massive structures form last. Small dark matter halos collapse first. They merge into intermediate halos. Those merge into larger ones. Galaxies form within these halos, their stars igniting from gas that accumulates over vast timescales through gravitational infall. It is a bottom-up process, building complexity from simplicity over billions of years. Webb's observations of the early universe show a cosmos that didn't get the memo. The tension between simulations and observations isn't limited to 6 objects. Webb's deep surveys have found an excess of massive, luminous galaxies at high redshifts across the board, meaning across all the epochs in the early universe that Webb has been able to examine. The problem isn't that a handful of outliers exist. The problem is that the entire population of massive early galaxies is larger, more luminous, and more structurally complete than the simulations produce. The simulations might be wrong about how efficiently gas converts into stars in the early universe. They might be wrong about how dark matter behaves at small scales. They might be missing some physical process that accelerated early structure formation in ways that the standard model doesn't account for, or the initial conditions of the universe. The density fluctuations that seeded all subsequent structure might have been different from what the CMB appears to indicate. Any one of these possibilities requires significant revision to the current cosmological framework. The data suggests it might be more than one of them simultaneously. There's a concept in cosmology called the stellar mass function, which is a statistical description of how many galaxies of each size exist at any given epoch in cosmic history. Webb's observations of the early universe have revealed a stellar mass function in the first billion years that doesn't match what the standard model predicts. There are too many large galaxies too early, and the discrepancy isn't marginal in some mass ranges and redshift bins. Webb is finding several times more massive galaxies than the best current simulations produce. This is the kind of quantitative, statistical mismatch that demands a theoretical response, not a footnote. Researchers who have spent careers building and refining these simulations are now openly discussing whether the fundamental assumptions baked into their models, assumptions about star formation efficiency, about feedback from black holes, about the properties of dark matter on small scales, need to be replaced rather than adjusted. The search for primordial black holes has a long and occasionally contentious history in physics. The concept was first proposed seriously in the early 1970s by Stephen Hawking and Bernard Carr, who showed mathematically that density fluctuations in the first fractions of a second after the Big Bang could, under certain conditions, exceed the threshold for gravitational collapse and form black holes directly from the primordial plasma. These objects would carry no memory of stellar evolution because they would predate stars by hundreds of millions of years. Hawking also showed, famously, that black holes should slowly evaporate through a quantum mechanical process, now called Hawking radiation, and that the smallest, Primordial black holes, those with masses comparable to asteroids or mountains, would have already evaporated entirely by now. But black holes with masses comparable to asteroids formed from those primordial fluctuations would still be here, invisible, drifting through the galaxy as part of the dark matter itself. The possibility that some fraction of dark matter consists of primordial black holes is one of the most actively debated questions in contemporary cosmology and particle physics. Decades of observational constraints, from gravitational lensing surveys, from the distribution of wide binary stars, from the chemical abundances of light elements produced in the first few minutes after the Big Bang, have ruled out primordial black holes as the sole component of dark matter across most of the plausible mass range, but they haven't ruled them out entirely. There remain mass windows where primordial black holes could constitute a significant fraction of the dark matter without contradicting any current observational bounds. And Webb's discovery of naked supermassive objects in the early universe has reignited serious theoretical interest in the high mass end of the primordial black hole spectrum. Objects formed not from asteroid-scale density fluctuations, but from region-scale collapses in the first seconds of cosmic time, emerging with masses potentially millions of times that of the Sun. If supermassive primordial black holes exist, their implications for cosmic evolution go far beyond simply explaining where the early universe's massive black holes came from. A population of supermassive primordial black holes scattered through the early cosmos would have served as gravitational seeds around which ordinary matter could preferentially accumulate, potentially accelerating the formation of the first galaxies and explaining why so many of the structures Webb sees in the early universe are more massive and more organized than simulations predict. They would have been the first significant gravitational attractors in a universe that was otherwise nearly uniform. The initial points of asymmetry around which the entire cosmic web of structure could begin to organize. In other words, if primordial black holes were common in the early universe, they may not just be an explanation for one of Webb's anomalies. They may be the explanation for several of them simultaneously. One of the quieter, but in some ways most profound discoveries Webb has contributed to involves the large-scale magnetic structure of the universe. The cosmic web, the vast network of dark matter filaments, gas sheets and galaxy clusters that organizes matter on the largest scales, has been understood in its gross gravitational architecture for decades. But the magnetic properties of the cosmic web had remained almost entirely uncharacterized because the fields involved are extraordinarily weak and require enormous sensitivity at the right wavelengths to detect. Webb, combined with radio observations from the largest current arrays, has begun to reveal that the filaments of the cosmic web are not merely gravitational structures. They are also magnetic structures, threaded with organized field configurations that have apparently persisted since the early universe. The magnetic fields Webb and complementary observations have detected in cosmic web filaments show a level of organizational complexity that standard models of how magnetism develops in the universe don't predict. Standard models assume that primordial magnetic fields, if they existed at all, would have been extremely weak and disorganized, tiny seed fields that only developed significant structure once stars formed and began injecting magnetic energy into the interstellar medium through stellar winds, supernova explosions, and the turbulent amplification processes associated with galaxy formation. The fields in the cosmic web filaments appear to have structure that predates most of those processes. They show organized patterns on scales far larger than any individual galaxy or cluster could have magnetized, suggesting either that the primordial magnetic seeds were more organized than standard theory predicts, or that some large-scale magnetization process operated in the early universe that current physics doesn't account for. The brain-like topology that researchers have noted when mapping these magnetic networks. The way the connectivity patterns of the cosmic webs, magnetic structure mathematically resemble the connectivity patterns of neural networks in biological brains, is worth pausing on, not because it implies any literal connection between cosmology and neuroscience, but because both systems appear to be solving a similar organizational problem: how to efficiently connect and distribute information or energy across a network with a fixed set of physical constraints. The universe and the brain arrived at superficially similar topological solutions through entirely different physical processes operating across incomprehensibly different scales. Whether that resemblance is meaningful or simply a consequence of the mathematics that describe efficient network organization in any medium remains an open question. But the fact that the same analytical tools developed to study brain connectivity are producing useful insights when applied to the cosmic magnetic web is itself a striking example of how deeply connected different domains of physical reality can be. The discovery of Jupiter mass binary objects raises questions that go beyond the specific puzzle of how they formed. The existence of hundreds of them in a single stellar nursery forces a reconsideration of what the total population of free-floating planetary mass objects in the galaxy might be. Previous estimates of rogue planet populations, based on gravitational microlensing surveys and statistical extrapolations from known planetary system architectures, suggested that free-floating planets might be roughly as numerous as stars in the Milky Way, perhaps 100 billion of them drifting through the galactic disk. Webb's census of the Orion Nebula, conducted over a relatively small area of sky, found numbers that push those estimates upward significantly. If the Orion Nebula's population of free-floating worlds is representative of stellar nurseries generally, the true number of rogue planets in the galaxy could be substantially larger than any prior estimate suggested. The radio emissions from certain JM-BO pairs remain one of the most technically fascinating and poorly understood phenomena Webb has contributed to identifying. The gigahertz frequency bursts coming from these worldless binary systems don't fit neatly into any known category of planetary radio. Emission, brown dwarfs, objects intermediate in mass between the largest planets and the smallest stars, are known to produce radio emissions through auroral processes driven by their strong magnetic fields, and the JMBOs are at the upper end of the planetary mass range, where brown dwarf-like magnetic activity becomes possible. But the binary nature of the JMBOs adds a complication that single brown dwarfs don't have. The orbital interaction between the two massive bodies generates tidal stresses and magnetic field coupling effects that have no analogue in any well-studied astronomical system. The result appears to be a unique electromagnetic environment in the space between each pair, a region where two massive magnetospheres interact, creating current systems and particle acceleration zones that produce radio signatures unlike anything coming from any single isolated object. What makes the JMBO radio emissions particularly worth paying attention to is what they suggest about the energetics of planetary magnetic fields under extreme conditions. The magnetic fields of the giant planets in our solar system, Jupiter, Saturn, Uranus, Neptune, are powerful by Earth standards, but are ultimately products of the specific internal structures and rotation rates of those particular worlds. The JMBOs appear to have magnetic fields substantially stronger than Jupiter's, driven by their larger masses, their rapid formation from high-density gas in the Orion Nebula, and the tidal pumping of their interiors by their mutual orbital interaction. If planetary mass objects can sustain magnetic fields this strong, the space environment around such worlds would be dramatically different from anything in our solar system, with radiation belts, magnetospheric structures, and plasma environments that would be intensely hostile to any conventional form of life, but equally intensely interesting from the perspective of physics operating in unexplored regimes. The case of 55 Cancri's atmosphere becomes even more remarkable when you consider what it implies about the history of that planet's geological evolution. A world that close to its star experiences tidal forces that would dwarf anything experienced by any world in our solar system. The tidal flexing of Earth by the Moon generates enough internal heat to contribute measurably to Earth's geological budget. The tidal flexing of 55 Cancri e by its host star, at a distance 18 times closer than Mercury orbits our Sun, would generate internal heat on a scale that makes the comparison meaningless. The planet's interior is almost certainly in a state of continuous, violent geological activity, not periodic volcanic episodes like Earth's, but a permanent condition of widespread melting and degassing that treats the distinction between crust and mantle as largely academic. This level of volcanic outgassing has implications that extend beyond the planet itself. The material continuously escaping from 55 Cancri's surface doesn't all stay in the atmosphere. A fraction of it is blown away by stellar radiation and winds, forming an extended tail of gas and mineral particles that trails behind the planet in its orbit. Webb's observations have detected signatures consistent with this escaping material, effectively documenting a planet that is slowly losing its own substance to space, not catastrophically, not rapidly in any human timescale, but continuously in a geological budget where mass is being both added by internal volcanism and subtracted by atmospheric escape. The planet is in a kind of dynamic chemical equilibrium between its interior and space, mediated by an atmosphere that is simultaneously being produced and destroyed. In 1 billion years, 55 Cancri will be a different planet chemically than it is today. In 10 billion years, it may have processed a significant fraction of its own crust through this cycle. It is, in the most literal sense, a planet that is slowly consuming and redistributing itself. The Sleeping Beauty galaxy phenomenon has a mirror image that Webb has also documented. Galaxies in the early universe that are doing precisely the opposite, forming stars at rates so extreme that they are consuming their entire gas supply in a fraction of the time that normal star-forming galaxies take. These starburst systems, forming stars at thousands of times the rate of a typical galaxy like the Milky Way, represent the other end of an apparent bimodality in early galaxy evolution. Some early galaxies burned through their fuel catastrophically fast and went quiet early. Others appear to have formed at normal rates and continued forming stars for much longer. What determines which fate a given galaxy followed is one of the most actively investigated questions in current observational cosmology. The starburst systems are connected to the Sleeping Beauty galaxies in a way that the data is beginning to make clear. The most extreme early starbursts, the ones consuming their gas at the highest rates, also tend to host the most actively feeding central, supermassive black holes. The relationship between star formation and black hole growth appears to be tightly coupled in the early universe in ways that models have only partially captured. As a galaxy undergoes violent star formation, the same gas reservoir that feeds the stellar nurseries also flows inward toward the central black hole, feeding it and causing it to grow. As the black hole grows, it eventually becomes active enough that its energy output, in the form of radiation and relativistic jets, begins to heat the surrounding gas. Once the gas is hot enough, it can no longer collapse to form new stars. The star formation shuts down. The galaxy goes to sleep. In this picture, the Sleeping Beauties may be the aftermath of the extreme early starbursts, the same galaxies, caught at a later stage of their evolution after their own central black holes grew large enough to end the party. The timing of this shutdown process and the question of what sets the clock for when it happens in any given galaxy is where current models break down. The feedback loop between black hole growth and star formation quenching is well established in principle. What isn't well established is why some galaxies quench very early, when the universe is only 1 billion or 2 years old, while others continue, forming stars for much longer. Dark matter halo mass is part of the answer. More massive halos accumulate more gas more quickly, forming larger galaxies with more central black hole growth, triggering earlier quenching. But the scatter around this trend is large, and Webb is finding quenched galaxies in halo mass ranges where the feedback models predict active star formation should still be occurring. Something else is operating in at least some of these systems, some additional quenching mechanism or some variation in the efficiency of the AGN feedback process that current models don't capture. The 48-hour monitoring campaign on Sagittarius A that Webb conducted represents one of the most intensive observations ever performed on our galaxy's central black hole, and its results are worth dwelling on in detail because they reveal how poorly we understand even the nearest supermassive black hole, the one we have the best possible observational access to. The brightness fluctuations Webb recorded span an enormous range. At the quiet end, the accretion disk produces low-level variability that could be attributed to relatively mundane turbulent processes in the superheated gas, magnetic field reconnection events, thermal instabilities in the plasma, and the chaotic fluid dynamics of materials spiraling at relativistic velocities toward an event horizon. These happen continuously, creating a baseline shimmer of varying intensity that never fully settles. The large flares are a different matter entirely. During the monitoring campaign, Webb recorded several major brightness increases that briefly made Sagittarius A dramatically more luminous than its baseline state, increases by factors of several within timescales of tens of minutes. The rapid rise and fall of these flares tells astronomers something important about their physical scale. Because the flare must be causally connected, the emitting region can be no larger than the distance light can travel in the duration of the flare. Flares that rise and fall in 20 minutes must originate from a region no larger than about 20 light minutes across, which at the distance of Sagittarius A corresponds to a region only a few times larger than the black hole's event horizon itself. These are events happening within a few Schwarzschild radii of the singularity, in a region where spacetime curvature is so extreme that the concept of a stable orbit barely applies, and where any matter caught in the wrong trajectory crosses the point of no return within hours. What's driving the flares at that scale remains genuinely contested. One model proposes that they result from magnetic reconnection events, sudden releases of magnetic energy that occur when oppositely directed field lines in the accretion disk are pushed together by turbulent flows and snap into a new configuration, converting stored magnetic energy into heat and radiation in seconds. This process is well understood in solar physics, where it drives solar flares on the surface of the Sun. But the energy scales near a supermassive black hole are many orders of magnitude larger, and the relativistic environment creates effects that have no solar analog. Another model suggests the flares mark the moments when discrete blobs of dense, hot gas in the accretion disk, called hotspots or plasma orbits, swing through configurations where their emission is maximally beamed toward Earth by relativistic effects, creating transient brightness spikes even if the intrinsic luminosity of the disk hasn't changed dramatically. Both models make testable predictions that Webb's continued monitoring is designed to distinguish between. Whatever the answer turns out to be, it will tell us something fundamental about how matter behaves in the most extreme gravitational environment accessible to human observation. The metallicity puzzle that Webb has uncovered in the early universe touches on one of the deepest questions in astrophysics. Where did the atoms that make up the physical world actually come from? The standard answer, that all elements heavier than hydrogen and helium were synthesized inside stars over billions of years and distributed by supernova explosions, is broadly correct, but Webb's observations suggest incomplete as a description of the early universe. The chemical enrichment timeline that the standard picture predicts for the first billion years of cosmic history doesn't match what Webb is actually finding. The early universe appears to have had more heavy elements sooner than the model allows. The hypothesis of extremely massive first-generation stars, sometimes called population 3 stars, has been theoretically developed for decades but has never been directly confirmed by observation because no population 3 star has ever been detected. These hypothetical stellar giants, formed from pure hydrogen and helium in the absence of any heavy elements, to provide the cooling mechanisms that regulate star formation in the modern universe, would have needed to be far more massive than any observed star to remain gravitationally stable during formation. Current models of star formation in pristine primordial gas suggest that population 3 stars might have ranged from a few dozen to perhaps several hundred solar masses, massive enough to live for only a few million years before dying in pair instability supernovae or direct collapse events that could enrich vast surrounding volumes with heavy elements in a single explosion. The signature of such enrichment events, a particular pattern of elemental abundances unlike what ordinary core collapse supernovae produce, is something Webb can potentially detect through spectroscopic analysis of the most metal-poor early galaxies. Whether those signatures are present in the data is currently one of the most actively analyzed questions in Webb-era observational astronomy. The implications of early chemical enrichment extend beyond the question of when stars formed. If heavy elements, particularly carbon, nitrogen, oxygen, phosphorus and sulfur, the elements most central to biochemistry, were available in the universe earlier than standard models predict, then the earliest possible epoch at which rocky planets with complex surface chemistry could have existed is pushed earlier. The current standard picture places the first potentially habitable rocky planets at roughly 1 to 2 billion years after the Big Bang, the time needed for sufficient heavy element enrichment to occur through multiple stellar generations. If Webb's observations are pointing toward earlier enrichment, the first chemically interesting rocky planets could have formed within the first billion years. And if rocky planets formed earlier, the window during which life, or whatever the universe produces in the direction of chemistry-driven complexity, could have first emerged is correspondingly expanded. The implications for questions about the prevalence and timing of complex chemistry and biology in the universe are substantial. The direct collapse black hole formation mechanism, illustrated by the infinity galaxy, but potentially operating far more broadly in the early cosmos, represents a solution to the early black hole mass problem that has the attractive property of being physically grounded rather than speculative. Unlike some proposed solutions which require invoking unknown physics, new particles, or exotic initial conditions, direct collapse from massive gas clouds is permitted by existing physics under the right conditions. The question is whether those conditions were actually met in the early universe frequently enough to account for the population of supermassive black holes Webb has found. The conditions required for direct collapse are specific and, in the modern universe, essentially never satisfied. The collapsing gas cloud must be massive enough, typically thought to require at least 100 million solar masses of material, and it must be prevented from fragmenting into stars during the collapse. In normal molecular clouds, the gas cools efficiently through molecular emission, developing temperature inhomogeneities that cause it to fragment into many smaller clumps, each of which collapses into individual stars rather than contributing to a single massive object. For direct collapse to produce a black hole rather than a star cluster, the cooling pathways must be suppressed, typically by the presence of an intense ultraviolet radiation field that dissociates the molecular hydrogen before it can facilitate efficient cooling. In the early universe, where massive stars and active galactic nuclei were more common than today, and where intergalactic radiation fields were correspondingly more intense, these conditions may have been far more frequently satisfied than they would be in the modern cosmos. Computer simulations of direct collapse black hole formation in early universe conditions have shown that, under the right radiation environment, collapsing gas clouds of the requisite mass can indeed bypass star formation entirely and produce black holes with initial masses of tens of thousands to potentially millions of solar masses, immediately in the supermassive range, with no need for billions of years of subsequent accretion to build up to that scale. If even a small fraction of the massive gas concentrations in the early universe underwent direct collapse rather than star formation, the resulting black hole population would be more than sufficient to account for every supermassive black hole Webb has found at early epochs. The infinity galaxy is showing astronomers this process in action, in real time, in a configuration where the conditions driving it, two massive gas reservoirs being slammed together in a high-velocity galactic collision, are visible and measurable. It is one of the most valuable natural experiments Webb has stumbled upon. The black hole cosmology hypothesis that our observable universe exists within the event horizon of a black hole in a larger parent cosmos is not a fringe idea. It has been developed seriously by a number of physicists, most notably Lee Smolin, who proposed it as part of a broader framework called cosmological natural selection, and Nikodym Poplawski, whose work on torsion in general relativity provides a specific mathematical mechanism through which the interior of a black hole could give rise to a new expanding spacetime. The basic intuition is simple. In general relativity, the interior of a sufficiently massive black hole is a region of spacetime that is gravitationally sealed from the exterior. No signal, no matter, no causal influence can cross the event horizon from inside to outside. From the perspective of an observer inside the event horizon, the boundary is invisible. It doesn't look like a wall or a surface. It is simply a region of space-time beyond which events can have no causal effect on the interior. If our universe exists within such a boundary, we would have no direct way to know it from the inside. The observable consequences would be subtle and statistical rather than dramatic and obvious, but they would exist. A rotating parent black hole would imprint angular momentum on the space-time of its interior, creating a preferred rotational direction that the large-scale structure forming within it would inherit. The initial expansion of the interior spacetime, what we call the Big Bang, would be driven not by a singular creation event, but by the dynamics of matter falling through the event horizon of the parent black hole, compressed and heated to extraordinary densities, and then expanding outward as the interior spacetime begins its evolution. The apparent acceleration of that expansion, which we attribute to dark energy, could result from the evolving geometry of space-time within the parent black hole rather than from any intrinsic property of empty space itself. What makes this hypothesis worth taking seriously, rather than dismissing as speculation, is the list of observational predictions it makes that Webb appears to be confirming. Coordinated galaxy rotations across scales too large for any causal mechanism to have produced them, consistent with inherited angular momentum from a rotating parent. Primordial black holes predating the first stars, consistent with objects that cross the parent black hole's event horizon, alongside the matter that would eventually form our universe. Expansion rate asymmetries that depend on the direction of measurement, consistent with motion through a space-time whose geometry has a preferred direction set by the parent black hole's spin. None of these predictions are unique to black hole cosmology. Each can be explained by other hypotheses as well. But the fact that a single framework accounts for all of them simultaneously, without requiring any new physics beyond what general relativity already permits, gives it a claim on scientific attention that grows stronger as each Webb observation adds another data point to the pattern. There is a temptation, when confronted with a list of anomalies and broken models, to conclude that science itself is failing, that the contradictions Webb has uncovered represent a fundamental crisis of knowledge rather than a frontier of discovery. This would be the wrong conclusion. What Webb is doing is what every great telescope in history has done. It is showing us that the universe is more detailed, more complex, and more rich with phenomenon than the instruments that preceded it could detect. Galileo's telescope revealed moons around Jupiter that shattered the crystalline sphere model of a perfectly ordered cosmos with Earth at the center. The development of spectroscopy revealed that distant stars are made of the same elements as the Sun, destroying the ancient assumption that the heavens were made of a different substance than Earth. The Hubble Space Telescope revealed that the expansion of the universe is accelerating, introducing dark energy as a concept and shattering the expectation of a cosmos that would eventually collapse back on itself under its own gravity. In each case, the shattering of the old picture was not a defeat for science. It was science working exactly as intended. Webb is operating in the same tradition at a far higher level of precision and depth than any predecessor. The models it is breaking are not naive or poorly constructed. They represent the accumulated intellectual achievement of generations of physicists and astronomers working with every tool available to them, tested against every observation possible before Webb came online. The fact that Webb is finding cracks in those models doesn't mean the models were worthless. It means they were good enough to make specific, testable predictions at the level of precision that earlier telescopes could reach. And now a better telescope has reached further and found the places where those predictions break down. This is, in the most straightforward sense, scientific progress. The models were approximations. The universe has more detail than the approximations captured. Webb is providing the data needed to build better approximations, ones that account for the additional detail that incorporate the early massive galaxies and the primordial black holes, and the coordinated galactic rotations, and the impossible feeding rates, and all the other anomalies that the first generation of cosmological models didn't need to explain, because no instrument could see them. The generation of theorists who will build those better models is working now. They have access to Webb's data in real time, and the observational constraints it provides are extraordinarily specific, not just a general sense that the early universe was different from expected, but precise measurements of stellar mass functions, spectroscopic metallicities, black hole mass estimates, accretion rate characterizations, and rotational alignment statistics at multiple epochs across cosmic time. These are not vague impressions. They are numbers, and numbers can be modeled, tested, refined, and eventually explained. The history of cosmology is a history of models that were broken by better observations and replaced by better models. Lambda CDM will be replaced by something that accounts for what Webb has found. Whatever that something turns out to be, it will be more accurate, more complete, and more genuinely descriptive of the universe as it actually is than anything that preceded it. That is not a catastrophe. That is how this works. The personal dimension of these discoveries, what they mean for any individual human being trying to understand their place in a universe revealed to be stranger and larger and more violent than previously described, is worth considering separately from the scientific dimension. Cosmological discoveries don't change the immediate texture of daily life. The Hubble tension has no practical consequence for anything that happens on the surface of Earth. The existence of primordial black holes drifting through the Milky Way doesn't affect the weather or the price of anything. But the picture of reality that science progressively assembles does matter in a broader sense, because it shapes what we understand ourselves to be and what we understand the context of our existence to be. The universe Webb reveals is one in which the familiar and comfortable occupy a smaller fraction of what exists than we previously thought. Most of what is out there, the dark matter, the dark energy, the rogue worlds, the primordial singularities, the structures operating on scales that make the entire observable history of human civilization invisible, is strange, is old, and operates according to physical principles that human intuition was not built to grasp directly. And yet here we are, grasping at it anyway. Building telescopes capable of detecting infrared light from galaxies that formed when the universe was a few 100 million years old. Analyzing spectra to determine the chemical composition of planetary atmospheres orbiting stars 40 light-years away. Measuring the rotation patterns of galaxies hundreds of millions of light-years distant to statistical precision, sufficient to identify coordinated motion that standard models say shouldn't exist. The human capacity for extended scientific inquiry, for accumulating knowledge across generations, for building instruments that transcend the limits of individual human perception, for constructing mathematical frameworks that describe phenomena no individual will ever directly witness, is itself one of the more extraordinary things that the universe has produced. Whether or not that matters in any cosmic sense is a philosophical question that physics is not designed to answer, but it is worth noting. The universe has, somewhere in its 13.8 billion year history, produced something capable of studying it, and that something is currently pointing one of the most sophisticated instruments ever built directly at the oldest and strangest and most problematic things it can find. Whatever those things turn out to be, they are going to tell us something real. One aspect of the Hubble tension that rarely gets discussed in accessible science communication is what it would mean if the resolution turns out to require not just a new cosmological ingredient, but a modification to general relativity itself. General relativity has passed every experimental test ever applied to it with extraordinary precision, from the bending of light by the Sun first, measured in 1919, to the decay rate of binary pulsar orbits, to the gravitational wave signals detected by LIGO from merging black holes and neutron stars. The theory's track record is essentially perfect across every scale and energy regime where it has been tested. But every one of those tests was conducted in the local universe, at redshifts close to zero, The Hubble tension is a discrepancy between measurements made in the local universe and predictions derived from the physics of the early universe, a comparison across cosmic timescales that general relativity has never been directly tested on. If the resolution requires modifying the theory of gravity itself at cosmological scales, the implications would extend far beyond cosmology and into every area of fundamental physics. Modified gravity theories, mathematical extensions of general relativity that introduce additional degrees of freedom or modify the behavior of gravity on large scales while preserving its successful predictions on smaller scales, have been proposed and studied for decades. Most of them were motivated by the desire to explain cosmic acceleration without invoking dark energy as a separate entity. Some of them also predict modifications to the expansion rate that could shift the CMB-based prediction of the Hubble constant upward, potentially closing the gap with the locally measured value. The challenge is that most modifications to gravity that are significant enough to affect the expansion rate at cosmological scales are also large enough to produce detectable signatures in the growth rate of cosmic structure, signatures that surveys of galaxy clustering and weak gravitational lensing have not found. The space of viable modified gravity theories is therefore narrowing under observational pressure from multiple directions simultaneously. Whatever the resolution to the Hubble tension turns out to be, it is unlikely to be a small or elegant adjustment to existing theory. The problem is too large and too precisely characterized for that. The jellyfish galaxy phenomenon illustrates something fundamental about the environment within galaxy clusters that is easy to overlook. The space between galaxies in a cluster is not empty. It is filled with a tenuous, extremely hot plasma called the intracluster medium that was heated to tens of millions of degrees by the gravitational energy released during the cluster's formation and by the shock waves from merging subclusters over billions of years. This plasma is so hot that it emits primarily in X-rays rather than visible light, making it invisible to ordinary telescopes but detectable by X-ray observatories. It is also, despite its extreme heat, dense enough in the cores of large clusters that a galaxy moving through it at typical cluster velocities, often several hundred to a few thousand kilometers per second, experiences significant drag. The ram pressure this drag exerts on the gas within the galaxy can, if the galaxy is moving fast enough relative to the intracluster medium, exceed the gravitational restoring force that holds the galaxy's gas to its stellar disk. When that happens, the gas is stripped. The stripping process is not instantaneous and not uniform. It preferentially removes gas from the outer regions of the galaxy's disk first, where the gravitational restoring force is weakest, before progressively working its way inward as the galaxy continues its high-velocity passage through the cluster. Webb's observations of jellyfish galaxies at multiple stages of this process have allowed astronomers to effectively watch RAM, pressure stripping in progress, and document how the stripped gas behaves once it leaves the galaxy. In many cases, the stripped gas doesn't simply disperse into the intracluster medium. It forms coherent, structured streamers and filaments that maintain their identity for tens to hundreds of millions of years after being removed from the galaxy, long enough to continue forming stars within the tentacles at significant rates. The cosmic owl and systems like it are therefore not simply being destroyed, they are redistributing their star-forming potential from a compact galactic disk into an extended network of tentacular structures that enriches the intracluster medium with newly formed stars and stellar feedback over a vast volume. The discovery of 3I Atlas as the third confirmed interstellar object provides a statistical baseline that astronomers have been waiting for since the detection of Oumuamua in 2017 established that interstellar objects do pass through the solar system. 3 confirmed interstellar visitors across less than a decade of systematic survey capability has allowed preliminary estimates of the density of such objects in the interstellar medium, the number of comets and planetesimals from other star systems per unit volume of galactic space. Those estimates, though still highly uncertain, are striking. They suggest that the interstellar medium contains vastly more planetary debris than any prior model of planetary system formation and evolution predicted. implying that planet formation is a much messier and more destructive process than the relatively orderly model built from studying our own solar system had suggested. The chemical diversity among the 3 confirmed interstellar objects is itself informative. Oumuamua was anomalous in almost every measurable property: its elongated shape, its lack of observable cometary activity, and its non-gravitational acceleration that some researchers attributed to radiation pressure on a thin solar sail-like structure. Comet 2I, Borisov, the second confirmed interstellar object detected in 2019, was more conventional. A carbon monoxide-rich comet that behaved essentially as expected for a typical cometary body from another stellar system, though with a notably high carbon monoxide abundance, suggesting origin around a star where the solar system's frost-line chemistry was different from our own. 3I Atlas, with its carbon dioxide-dominated coma and ancient age, adds a third distinct chemical type to the emerging catalogue. The emerging picture, even from just 3 data points, is one of significant chemical diversity among planetary systems throughout the galaxy, consistent with what Webb's observations of protoplanetary disks like XUE-1 are revealing about the range of chemical environments in which planets form. The extreme gravitational lensing system Webb documented, producing at least 4 distinct images of a background galaxy, each showing the source at a different moment in its evolutionary history, represents a type of observation that has profound practical value beyond its inherent scientific interest. The time delays between the arrival of light along different lensed paths are directly sensitive to the expansion rate of the universe. Light traveling along a shorter, less curved path arrives before light that has taken a longer, more curved route from the same source, and the magnitude of that time difference depends on how fast the universe was expanding along each path, which depends in turn on the Hubble constant. This technique, called time delay cosmography, has been used with quasar lensing systems for decades as an independent method of measuring the Hubble constant. It consistently produces values in the range of 73, consistent with the local measurements from Cepheids and Type supernovae, and inconsistent with the CMB-based value of 67. The lensing system Webb discovered by providing time delay measurements of unusual precision in a system where the source galaxy's evolution can be directly tracked across multiple epochs adds another data point to this already troubling pattern. The dark matter substructure revealed by the lensing geometry of this system, the clumps and density variations within the dark matter halo of the lensing galaxy that standard smooth halo models don't predict, connects to one of the deepest unsolved problems in dark matter physics, the small-scale structure problem. Standard cold dark matter theory predicts that dark matter halos should contain enormous numbers of subhalos, smaller concentrations of dark matter, embedded within larger ones in a hierarchical fashion extending down to extremely small scales. The number and distribution of these predicted subhalos doesn't match what is observed in the local universe. Galaxies like the Milky Way have far fewer satellite galaxies than the predicted number of subhalos would suggest. Either most of the predicted subhalos exist, but failed to form visible galaxies within them, perhaps because their small masses made them too shallow for gas to accumulate, or the dark matter distribution on small scales is genuinely smoother than standard cold dark matter theory predicts, which would require a modification to the standard dark matter model. The substructure Webb's lensing analysis reveals in the halo of the lensing galaxy provides a new way to count dark matter clumps directly without relying on the number of satellite galaxies as a proxy. The results will have direct implications for what kind of particle dark matter is. The kilonova events that Webb has documented, the explosive mergers of neutron stars, and the mergers of neutron stars with stellar mass black holes, carry significance that extends well beyond their immediate astronomical interest. The elements produced in kilonovae are not merely exotic byproducts of extreme astrophysical events. They are the origin of a substantial fraction of the material world: gold, platinum, iridium, osmium, palladium, rhodium, tellurium, iodine, elements heavier than iron that cannot be synthesized in the interiors of ordinary stars or even in ordinary supernova explosions, are, produced primarily in the extreme neutron-rich environments created during compact object mergers. Every piece of gold jewelry ever made, every circuit board containing gold traces, every tooth filling with gold alloy, every gold coin ever minted across all of human history, the gold in every one of them was forged in a kilonova explosion that occurred billions of years before the solar system formed. Webb's documentation of these events in progress, capturing the optical and infrared signatures of freshly synthesized heavy elements expanding outward from merger sites at fractions of the speed of light, is in a literal sense watching the universe manufacture the materials that complex chemistry and biology depends on. The rate at which the universe produces these elements, and whether that rate has changed over cosmic history, has direct implications for the availability of the chemical building blocks needed for complex planets and chemistry. If kilonova events were more or less frequent in the early universe than today, or if they preferentially occurred in certain types of galaxies, or at certain stellar population ages, the distribution of heavy elements across cosmic time and galactic environments would be non-uniform in ways that affect the probability of complex chemistry at different epochs. Webb's ability to detect kilonova signatures across large cosmic distances, and therefore across large spans of cosmic time, is beginning to provide the observational dataset needed to address these questions directly. The early indications suggest that neutron star mergers may have been somewhat less common in the very early universe, when stellar populations were younger and the time available for neutron stars to inspiral and merge was shorter. If true, the heavy element inventory of the early universe may have been even more limited than standard chemical evolution models suggest, further constraining when and where the conditions for complex chemistry could first have been established. The darkness of interstellar space has, over the course of human intellectual history, consistently turned out to contain more than the best available model predicted. The ancient picture of fixed stars embedded in crystalline spheres was replaced by a universe of vast distances and independent suns. The assumption of an unchanging, eternal cosmos was replaced by the discovery of an expanding universe born in a single event of extraordinary energy. The belief that our galaxy was the entirety of the cosmos was replaced by the recognition that it is one of hundreds of billions. The assumption of a universe, decelerating under its own gravity, was replaced by the discovery that the expansion is accelerating, driven by something we call dark energy, but do not understand. At every stage, the instruments got better, and the universe got bigger and stranger. Webb is continuing that tradition at a level of capability that would have seemed fantastical to the generation of astronomers who built Hubble. The universe it is revealing is, as every previous expansion of observational capability has revealed, more complex, more structured, more historically rich, and more physically surprising than the model it is replacing. What is different this time, perhaps, is the scale of the surprises. Previous expansions of observational capability typically revealed that the universe was larger, or older, or more numerous in its constituents than previously understood. Discoveries that extended familiar categories into new territory. Webb is finding things that don't fit existing categories at all, objects that have no modern analogues, processes that violate the predicted maximum rates of physical phenomena, structures whose formation cannot be accounted for by the available time and the known physics. The difference between a universe that is merely larger than expected and a universe that behaves differently than expected at fundamental levels is significant. Prior expansions of observational scope required extensions of existing models. What Webb is generating may require replacements. The models that will emerge from this generation of observation may not look like refined versions of lambda CDM. They may look like something genuinely new, and genuinely new models of the universe, frameworks that reorganize how we understand the relationship between space, time, matter, and energy, are among the rarest and most consequential intellectual achievements in the history of science. If you made it to the end of this, you now know more about the state of observational cosmology than most people alive. The discoveries Webb is making don't have simple summaries. They don't reduce to a headline or a bullet point. They require the kind of detailed engagement with evidence and implication that you've done here. The universe is not simple, and understanding it isn't simple either. But the effort is worth it, not because it has practical applications, though some of it eventually will, but because understanding what is real is valuable in itself. The night sky looks the same whether you know what Webb has found or not. But knowing what's out there, knowing that the light from those points and smears has been travelling for billions of years, that some of those faint smudges contain structures that assembled faster than any model says they should have, that somewhere out there ancient black holes are drifting that have existed since before the first star ever burned, changes how the sky feels. That's not nothing. That might in fact be everything. The concept of galaxy quenching, the transition from active star formation to dormancy, has a population-level statistical signature that Webb is now measuring across cosmic time with a precision that no previous instrument could achieve. Astronomers describe the relative proportion of star-forming versus quiescent galaxies at any given epoch as the quenched fraction. In the local universe, the quenched fraction among massive galaxies is high. The majority of the largest galaxies in the modern cosmos formed the bulk of their stars billions of years ago and have been relatively quiet ever since. In the early universe, theory predicts that the quenched fraction should be lower because the mechanisms responsible for quenching, AGN feedback, environmental effects in cluster cores, gas exhaustion, need time to operate. Webb's measurements of the quenched fraction at high redshift are producing values significantly higher than simulations predict. More galaxies are quenched earlier than the models allow. This is another version of the same broad pattern. The early universe assembled its large-scale structure faster and reached more evolved states sooner than current cosmological models can explain. The environmental dependence of quenching provides additional texture to this picture. In the local universe, galaxies in dense cluster environments are more likely to be quenched than galaxies in the field, an effect attributed to processes like ram pressure stripping and strangulation, the cutoff of the cold gas supply from the cosmic web that feeds star formation in isolated field galaxies. Webb's observations at high redshift are revealing that this environmental dependence of quenching was already present when the universe was only a few billion years old. The overdense regions in the early cosmic web were already preferentially shutting down star formation in their galaxy populations at a time when those overdensities had only recently become distinguishable from the surrounding cosmic average. The seeds of the relationship between environment and galaxy evolution were apparently planted very early, and they grew into the full pattern we see in the local universe through a process that operated consistently over most of cosmic history. Webb's observations of galaxy clusters at high redshift have also revealed the properties of the intracluster medium at earlier cosmic times, when the clusters were still assembling and the plasma filling their interiors was being heated by the gravitational energy of ongoing accretion. In mature local clusters, the intracluster medium has had billions of years to reach a kind of approximate thermodynamic equilibrium with temperature structures and density profiles that are relatively well characterized by standard models of gravitational heating and cooling. In the early protocluster environments Webb is observing, the intracluster medium is in a more chaotic state, being continuously energized by infalling galaxy groups and streams of gas from the surrounding cosmic web, laced with shock waves from merging subclusters, and enriched with metals expelled from cluster galaxies by supernova winds and AGN jets on timescales that Webb can partially resolve. The thermodynamic history of this plasma, how it was heated, how it was enriched, how it achieved its current state, is encoded in its current temperature and abundance profiles, and Webb's observations of young clusters are providing the early chapters of that history for the first time. The question of what dark matter actually is, what kind of particle or collection of particles constitutes the 85% of the universe's matter content that produces gravitational effects without any detected electromagnetic signature, remains one of the most important unsolved problems in physics. Webb's contributions to dark matter science are primarily indirect, by providing precise measurements of gravitational lensing, of galaxy rotation curves in the early universe, and of the structure and distribution of dark matter halos across cosmic time. Webb is constraining the properties that any viable dark matter candidate must have. The small-scale structure observations, the evidence of dark matter substructure within galactic halos from gravitational lensing, and the general distribution of satellite galaxies around large galaxies are particularly informative. Standard cold dark matter, composed of slow-moving particles that cluster freely on all scales, predicts more small-scale structure than is observed. This discrepancy has motivated alternative dark matter models, including warm dark matter, in which the particles have higher thermal velocities and therefore a minimum scale below which they cannot cluster, and fuzzy dark matter, in which the dark matter is composed of ultralight bosons with quantum mechanical wavelengths large enough to produce observable suppression of small scale structure through quantum pressure rather than thermal motion. Each of these alternative dark matter models makes specific predictions for the distribution of dark matter on the small scales that Webb is now able to probe through gravitational lensing and the statistics of faint satellite galaxies at high redshift. If the dark matter is warm rather than cold, there should be fewer small dark matter halos, fewer satellite galaxies per host halo, and smoother dark matter distributions within halos than cold dark matter predicts. If the dark matter is fuzzy, the predictions are similar but with a distinctive scale-dependent signature, a sharp cutoff in the power spectrum of density fluctuations at the de Broglie wavelength of the dark matter particle, that is, in principle distinguishable from the thermal suppression of warm dark matter. Webb cannot directly detect dark matter particles, but it can measure the gravitational consequences of their distribution with sufficient precision to discriminate between these models. The data currently being accumulated by Webb's surveys of gravitational lensing and high redshift galaxy statistics will be among the most powerful constraints on dark matter particle properties available in this decade. There is one final thing worth saying about the James Webb Space Telescope that gets lost in the avalanche of individual discoveries. The instrument itself represents an extraordinary achievement of collective human technical capability. Webb was conceived in the 1990s, formally proposed in 1996, approved in 2002, and launched on December 25, 2021. After decades of development, multiple design revisions, catastrophic budget overruns, and near cancellation on at least 2 separate occasions. It is the product of contributions from thousands of scientists, engineers, and technicians working across NASA, the European Space Agency, the Canadian Space Agency, and dozens of universities and research institutions over more than 2 decades. It operates at a temperature of under 50 Kelvin, colder than most of the universe, sustained by a 5-layer sunshield the size of a tennis court that must be deployed in space with perfect reliability from a folded configuration that fit inside the launch vehicle. Every one of its 18 primary mirror segments had to be aligned to within a fraction of a wavelength of light after deployment. It was designed to last 10 years but is expected, based on its precise launch trajectory, to have fuel for significantly longer. By every technical metric, it is the most complex scientific instrument humanity has ever placed in space. And it works perfectly. The universe it is showing us is the universe as it actually is, not filtered through the limits of previous capability, but exposed in its full strange detail for the first time. That is what Webb is, and it has only just begun. The universe Webb is revealing has a quality that is easy to miss if you focus only on the anomalies and the broken models. It is extraordinarily consistent, not consistent in the sense that it matches our predictions. It demonstrably doesn't, in a growing number of important ways, but consistent in the sense that the anomalies themselves form patterns. The early universe is systematically more structured, more chemically enriched, and more populated with massive compact objects than the standard model predicts. The expansion rate is systematically higher in local measurements than in CMB-based predictions. Galaxy rotations are systematically correlated across scales that exceed any local causal mechanism. These aren't random scatters around expected values. They are coherent deviations that point in consistent directions across multiple independent measurement techniques. That coherence is a signal. It is telling us that the standard model is not randomly wrong, it is wrong in specific ways that may ultimately be traceable to a single missing ingredient or a small set of related ones. Finding that missing ingredient is the central scientific challenge that Webb has placed in front of the next generation of theorists. One of the most practically significant aspects of Webb's scientific program, beyond its contributions to fundamental cosmology, is what it is revealing about the diversity of planetary system architectures and atmospheric chemistries throughout the galaxy. The telescope was designed with exoplanet atmospheric characterization as one of its primary science goals, and its NIRISS and NIRSPEC instruments have been used to dissect the atmospheric compositions of dozens of worlds orbiting other stars in transmission spectroscopy observations, watching starlight filter through a planet's atmosphere as the planet transits its host star, and analyzing the wavelength-dependent absorption to identify molecular constituents. The results have been both confirmatory and surprising. The detection of carbon dioxide in the atmosphere of a hot Jupiter several years ago was a confirmation of expected chemistry. The detection of sulfur dioxide produced by photochemical reactions in another hot Jupiter's atmosphere was unexpected. A molecule whose presence requires ultraviolet photochemistry operating in conditions that models had not accurately predicted. The XU-1 protoplanetary disk chemistry adds a third category, a planet-forming environment that produces worlds whose bulk composition will differ from any atmospheric chemistry template built around solar system analogues. The galaxy Webb's observations suggest is in the business of making a much wider variety of worlds than any single reference system could have taught us to expect. Everything Webb has found points toward the same underlying conclusion, stated as plainly as possible. The universe is older in its violence, richer in its structure, and more varied in its physical processes than the most sophisticated models built before this telescope came online were able to capture. That conclusion is not a condemnation of those models. It is an accurate description of where we are in the scientific process, at a transition point between one level of understanding and the next, equipped for the first time with an instrument capable of testing ideas at the scales where they actually matter. The transition points are where science does its most important work. The comfortable periods of model confirmation are valuable. They build the quantitative foundation that makes the next transition possible. But the moments of genuine anomaly, of coherent systematic deviation from expectation, of the universe behaving in ways that force the current framework to its breaking point, those are the moments that produce the deepest revisions in understanding. We are living in one of those moments right now, and the instrument producing it is pointing at the sky tonight, collecting light that has been traveling for billions of years to reach it, and turning that ancient light into the most detailed and honest portrait of reality that human beings have ever made.